Okay, so you too, man. We are going to pick up on slide number 18. We've been talking about friction. And so friction is the rub-a-dub-dub of my, there's three types. We said that there's static friction where the objects are not actually able to move past each other. So there is no motion. So even though like you might be pushing, you might be pulling, you're not going to be able to overcome the friction that is holding or keeping that object in place. So like my table, I push it, I'm applying a force, but it's wiggling, but I can't get it to move. There's too much static friction between the table and the floor, right? I would need to apply more force or like have it on wheels or like put some oil underneath it so I could get it to slide easier, right? There's things you could do, but it's not moving at this point. So it is experiencing static friction. We also said that there's sliding friction where objects slide past each other, right? And so I give it a little push and the book moves. I give it another push and it moves. If I keep my hand on it, I can feel kind of continuously, like I can hear it as it slides. I can feel it almost kind of gripping underneath. But I still am able to get it to move, right? One thing that I want to say from yesterday with the normal force, I want to back up because there was something I kind of forgot with you guys. Sorry. So I know, shocking. I'm a terrible morning person, so sometimes I struggle with you guys. And so I'm backing up. With normal force, we said that it's going to work perpendicular, right? So let me use this one. If this is my surface and this is my normal force, as the surface changes, the angle of my normal force changes. So if it's like this and gravity is pulling downward, they're not perfectly canceled out. If the surface is flat, they're canceled. But if you're on an angle, a hill, a slope, then they're not canceled. And so that's why it feels like gravity is stronger. That we covered pretty well yesterday. The thing that I had said is that you're not like cranking gravity up, right? It's not that you've changed gravity's strength. We can't really do that, right? What has changed is that they're not canceled. Here they are, on a slope they're not. The opposite is also not true. There isn't a situation where we decrease gravity or crank up normal force, because normal force is the force pushing up. So all of you are sitting in a chair right now, right? And so I've never seen where students just randomly start levitating out of their seat, right? This book isn't just going to randomly start floating. The normal force is never going to be stronger than the gravity where it's like, whoop, it's defying gravity. That's never happened. Never experienced it. Maybe in our lifetime something will change that, I don't know, but up until this point, it's never happened. So that is something that I didn't mention. Like a lot of times we can feel like gravity is stronger, like when we're walking up a hill and we feel like it's pulling us back. But the opposite is also not true, where normal force feels stronger. Like that doesn't happen. It doesn't get to where like gravity feels less and normal force feels more. So I just kind of wanted to point out that example as well. So the forces themselves are staying constant. It's just like they're not canceling out, or are they canceling out? And so that's the difference. Canceling out, not canceling out, right? And so I just wanted to kind of backtrack for a second and make sure I explained that part of it. Right? Which is, I mean, it's kind of an easy idea because we know it doesn't happen, right? You guys, we don't just start levitating. When you have a solid to a solid, you know, we know that the solid object isn't going to just start randomly floating, okay? So the final friction, back to slide number 18, is something called rolling friction. And this actually revolutionized our world, this idea of a wheel or something that can roll. We take it for granted, but a tire, a wheel, something round has not always been kind of like our go-to method, like in the history of humans, right? It had to be discovered, it had to be like developed, like, oh my gosh, this really helps, right? And so rolling friction usually requires less force, and it allows the object to continue to move for a longer period of time, typically. So if I have this book, and I give it a little tap. It moves a little bit, right? Not too bad. If I would put it on these straws, and I'm going to try to give it about the same tap or the same amount of force, it goes quite a bit farther, okay? Much easier, much smoother kind of slide along the table, right? If you think about it, when I push it like this, the entire surface of the book is in contact with the table, the whole side of it. When I have the straws underneath, the only place that is touching the book is that thin line, not the whole straw, right? Just like a single line down each straw. So you have these single lines of contact with the book, but you don't have like the entire surface contacting the book all at one time. And by reducing that surface area that's in contact with now we're kind of changing the surface to the straws instead of the table, it reduces the amount of friction, and so it allows that object to slide more freely, and we actually call that rolling friction. When anytime there are wheels, and you can see they put pencils in a book, anytime you're dealing with something that has something round underneath it, or wheels or tires or something like that, you're dealing with rolling friction. Okay? Make sense? Okay, so those are 3 types of frictions that involve contact, right? Because obviously the table is in contact with the floor for static friction, where I can't get that table to move. And then sliding friction, the book is in contact with the table, right? As I give it a little push and it slides. And then the book has to be in contact with the straws as I give it a little push for my rolling friction. All of those are at contact for sure, right? Most of the time we're talking like a solid to a solid contact as well. There's some other frictions obviously that are involved, and we talked about those a little bit yesterday. The idea of drag, where something is moving through a gas or a liquid, and there's gas all around us, right? Air is a gas, and we live in a gaseous environment, which is good because that allows us to live, which is always a good thing. So everything here on Earth is moving through a gas if it's moving here on Earth, right? And so everything is going to experience some form of drag, if it's in motion, right? And so we're going to take a look. Let me think here. I'm going to stop this I think I want to stop this for a second. Yeah, give me 1 second. Let me check something real quick. Okay. We're going to go just a couple clicks. I need to make sure I didn't go too far. Okay, so when we know that something is in free fall, gravity is what's responsible for pulling it down. That is not a shockingly new piece of information, right? But there's something called lift, right? Air will get underneath the object and lift it up or cause air resistance. So as the object is falling, air can resist the object falling. That also probably shouldn't be something shocking. So if I take a piece of paper and I drop it, right? It's going to kind of float down. Air is going to catch and lift under. What's going to happen if I take the same size paper, but I crinkle it up, turn it into a ball? Is it going to fall to the tabletop also? Sure, right? So if I drop them both at the same time, which one do you think is going to land first? What? The ball. not even close. They have the same mass, it's the exact same piece of paper. All I've done now is change the shape. By changing the shape, what was really being affected? What do you think? There?
Aerodynamics?
Yeah, like, well, fanciness. Sure, what'd you say? We didn't change the gravity, right? Gravity had to stay the same. But what did this have more of?
I can't remember what it's called. That's what I was just about to say.
Yeah, surface area.
Surface area, right? It has more area to catch air. This has a lot less area. So these have the same mass, but gravity seems like it's pulling on them differently, which you're right, it does seem like gravity was changed. Could this have one set of gravity and this have another set of gravity though? No, gravity has to be pulling on all objects equally. But there are factors like air resistance or surface area of an object that will have an effect. And so just like with our normal force, where most of the time, you know, if it's on a flat surface, the gravity is going to cancel out the normal force. But if it's on an angle, the normal force does not get canceled out, right? Or excuse me, the gravity does not get canceled out. And so it feels like gravity is more. So there's a lot of situations where it feels like gravity is being changed, when really it's consistent. It's just there's some other explanation of why. And here, the explanation is surface area. It catches more air, so there's more air resistance. Obviously, this is a good thing if you are jumping out of a plane and you have a parachute, right? You want that parachute to catch the air. The resistance that air places on objects we call air resistance, which is a special type of drag, which is a special type of friction. Okay, and so the force of air resistance is going to be in the opposite direction of the force of motion. Well, yeah, because that's the definition for friction. If motion is down, friction is going to be up. They're always opposites. And so the amount of air resistance is going to depend on the size and the shape of the object, which we demonstrated with the flat paper versus the crumpled up paper. Same mass, different effect on how it fell. Okay? All right, so we're going to watch a couple little things. Some of these videos are, actually this one video is one of my favorites.